It's time for the third installment of my tutorial for 65816 assembly language on the C256 Phoenix. And today I want to cover how you can reuse code in 65816 assembly. This is going to involve subroutines and macros. And along the way I'm also going to cover the 65816's stack, since that will be needed for subroutines. To start, I want to talk for a moment about how memory is organized by the 65816. The system's address space is divided up into banks, each of which is 64 kilobytes in size. When you look at a 24-bit address, the upper 8 bits are the bank number, and then the lower 16 bits are the address within the bank. These banks reflect the original 64 kilobyte address space of the 6502 processor that the 65816 is based on. And the very first bank, bank 0, is special. There are certain addressing modes that will only work in bank 0, not any of the other banks. And when the 65816 is in what's called emulation mode, where it's pretending to be a 6502, bank 0 is the entire address space of the processor at that point. Now, there are two data registers in the 65816 that refer to memory banks in some way or other. One is the data bank register B, and then the other is the program bank register K, which can also be seen as just being the upper 8 bits of the program counter. So K is holding the bank of the code that is currently running. The 65816, like many processors, provides a stack. Now, if you're not familiar with what a stack is a type of data structure, a way of storing data, that lets you do two things. You can push data onto a stack, or you can pull data off of a stack. And stacks are what are called last in, first out, or LIFO structures, in that you pull data out in the opposite order that you put it in. So when you push data in, the last thing you push is the first thing that you can pull. The stack on a 65816 can be stored anywhere in bank 0, and it's supported by a special register called the stack pointer. The stack pointer points to the address in memory where the next byte will be pushed. So when a byte is pushed onto a stack, it's stored at that location that's indicated by the stack pointer, and then the stack pointer is decremented by one value. The stack in the 65816 grows down in memory. That is, it grows from higher addresses down to lower addresses, which may seem a little strange, but it works. Now, when a byte is pulled from the stack pointer is then incremented, and then the data at that address is copied into the destination register. And when you're pushing or pulling values, you can push either 8-bit or 16-bit values. And when that is happening, then the stack pointer is incremented or decremented by 2 positions. And it always pushes the data so that the high byte is put in the higher address than the low byte. So it's storing values, as happens in other places in the 65816, in little endian format. That is, the lower, least significant bits are placed on the lower address, and then the most significant bits are stored in the higher address. Now, 7 registers can be pushed onto the stack. The accumulator with PHA or push A, the 2 index registers X and Y with push X and push Y, and then 4 different control registers: the processor status register with PHP, the data bank register B with PHB, a special register D that we haven't talked about yet but will soon with PHD, and then the code bank register K with PHK. So I'm not going to go into each one of these instructions. I'm just going to want to look at PHA for the moment. The rest all work in a fairly similar manner. So since the accumulator can be either 8 bits wide or 16 bits wide, we have 2 different examples that I've shown here. On the left, we have a case where the stack pointer starts off at 001FFF, and we push the 8-bit accumulator, which has the value in hexadecimal of 12. And after we push, the memory location 001FFF has the value 12 in it, and the stack pointer is then decremented and pointing at 001FFE. On the right, we have the 16-bit case. Now there, the accumulator has the hexadecimal value 1, 2, 3, 4. And after the push, 1, 2, 3, 4 is stored in memory. The 1, 2 part is again up in 0, 0, 1, F, FF. The 3, 4 part is down in 0, 0, 1, F, FE. And then the stack pointer is now down at 0, 0, 1, F, FD. So you see that the stack pointer has been decremented twice as part of that push. And again, the value of the accumulator pushed into memory is written down in Little Endian format, which is convenient because then we can read that with other 16-bit instructions in a fairly natural order. I should mention there are some additional push instructions, but since I'm not going to use them today, I won't get into their details right now. We'll probably look at them a little bit later in a later tutorial when we start looking at some more advanced coding techniques. Now, as for pulling data back off the stack, there are 6 instructions to pull data into registers. We have 3 instructions for the common registers that we've used before, the accumulator and the 2 index registers, and those instructions are PLA for the accumulator, PLX for the X register, and PLY for the Y register. These instructions, as before, can be either 8 or 16 bits depending on the size of those registers. And then we have 3 instructions for the different control registers. PLP to pull the processor status register, PLB to pull the databank register, and PLD to pull that D register that we'll talk about again in the future. Note that there is no pull instruction for the code bank register. It really wouldn't make sense to have that because that would then change in a strange way where your code is executing. And also there are no pull instructions into random memory locations, and there are also no pull instructions that simply throw data away from the register. So these are the only pull instructions that we have. The other thing I should note here is that the 65-bit16 makes no attempt to make sure that the data you're pulling into a register originally came from that register or even makes sense to go into that register. So you can push a value from A and pull it into B. You can push a value from B and pull it into the processor status register, all sorts of strange things like that. So your code's going to have to be a little careful to make sure that it's pulling data that it's meant to be pulling into a particular register, something that's appropriate. Now, I need to pause for a moment here and talk a little bit about how you read the manual. I can't possibly cover every single detail about the CPU and about these instructions. There's a lot of information that you need to have. And so from time to time, you're going to have to refer to the official documentation and the data sheets and so on to understand exactly what a particular instruction is going to do. So I want to show you an excerpt from a book called Programming the 65-bit16 to give you a feel for what sort of information you can expect from the reference materials. This particular book comes from the Western Design Center, so it's from the people who know this processor. And I'll put a little link to the book in the documentation, in the description for the video, so you can go and pick up a copy yourself. So what we have here is a description from the book of the PLA instruction so that you can see how it's structured. Now, you can see at the top is a prose description about how the instruction works, including the sequence of when the stack pointer is incremented and when the data is copied from the stack. And it also talks about the 2 cases that the PLA will do of an 8-bit pull versus a 16-bit pull. Below that, you see a listing of the flags that are affected by this instruction. Now, I mentioned in a previous tutorial that instructions don't always affect all of the flags in the processor status register. And it can be important to know what flags are affected by an instruction when you're using it. And in this case, PLA will alter the N and the Z flags. So if the number that you've pulled has got the most significant bit set, so it's can be considered a negative value, N will be set. If it's clear, then N will be clear. And the Z flag, again, reflects whether or not the value is 0. So if you pull a 0 out of the stack, then PLA is going to set the 0 flag. But those are the only two flags that are going to be set here. The rest are going to be left unchanged by the instruction. So carry, the overflow bit, the interrupt control bit, all that sort of stuff. That's all going to be left alone by PLA. And then finally, at the bottom here, there's a table. And normally what this would be doing is listing out all the different addressing modes on this instruction. So all the variations of the instructions based on what addressing mode it's using. Now there's only one for PLA, so we just have the one line here. But what it will show is the opcode for a particular addressing mode, what chips in the family of processors support this instruction, how many bytes the instruction requires in the code, and how many clock cycles it will take to execute. Different addressing modes have different levels of complexity for the processor, and so an instruction might take a different number of cycles depending on which addressing mode you're using. And if you're writing really tight code in terms of the timing, it's very important to know how many clock cycles that's taking up. For a lot of stuff, it won't really matter, but sometimes you're writing a really tight loop or you need to get the timing exactly right in a certain piece of code. And this can tell you exactly how many clocks that instruction is going to take to execute. So let's talk about subroutines on the 65816. And to use slightly different terminology, what I'm talking about here really are things like procedures and functions. Now, there are two types of subroutines that the CPU supports. There are what are called near subroutines, which are stored in the same bank of memory as the code that's calling the subroutine. And there are far subroutines that can be stored anywhere in memory. And the reason this is important is that these two different types of subroutines are called by different instructions. A near subroutine is called with the JSR instruction, which takes the address of the subroutine to be called as the operand. When the subroutine that's called by JSR needs to return to the caller, it has to execute the RTS instruction. A far subroutine is called with the JSL instruction, which can be considered like jump to subroutine long. Long is another term for far. And when that kind of subroutine returns, it has to execute the RTL instruction. And it's a big problem if your code tries to call a far subroutine using JSR or a near subroutine with JSL. You simply cannot mix near and far calls in that way. One consequence of this is that code cannot directly call a near subroutine from a different bank of memory, although a near subroutine can call out to a far subroutine quite easily. So let's take a look at how these instructions work to explain why this is. When JSR is executed, it takes the current program counter and pushes it to the stack to be retrieved later. Because it is a near subroutine that's being called, only the lower 16 bits of the program counter are pushed to the stack. So you can see an example here on the lower left. There we have a JSR instruction at 010000 calling out to a subroutine at 010100. The program counter value of 0002 is pushed to the stack. The reason for this is that at the time JSR is executed, the program counter is pointing to the last byte of the JSR instruction. Now, when RTS is executed, it pulls 16 bits off the stack and increments that by 1 and then puts that value into the lower 16 bits of the program counter. And that will then start it executing the instruction right after the JSR. JSL, on the other hand, pushes a full 24 bits of the program counter onto the stack. You can see an example here on the right. That's got a JSL at location 0100 calling out to a subroutine at 020100. You can see that in this case, the full program counter value of 010003 was pushed to the stack. Again, that's pushing the address of the last byte of the JSL instruction. And since JSL can call out to any address in memory, JSL takes 4 bytes, 1 opcode, and then 3 for the operand. RTL, that goes along with JSL, will try to pull 24 bits off the stack and use that for the entire program counter. Now, you can see here that both RTS and RTL have to assume how much program counter data is on the stack. And if that assumption is incorrect in either case, the return is likely to go to the wrong location in memory. And will probably confuse the stack as well by either pulling too little data or too much data off of the stack. Now, there's one final item I want to talk about today, and this is an assembler feature called macros. So let's say that you have a set of assembly code that you want to be able to reuse multiple times in a program, but for whatever reason it can't really be a subroutine. Either it's too costly to do as a subroutine, too inefficient to use as a subroutine, or maybe it's using some sort of construct that you can't really use in a subroutine, or use something with a stack or whatever, various reasons. Rather than typing that code out multiple times, would you like to have some sort of shorthand? And that's what a macro is for. When you define a macro, you give a name to a block of assembly code. And then when you invoke that macro somewhere else, that line where you invoke the macro is replaced with the block of assembly that's inside the macro. And that macro can actually, in some cases, take parameters so that when you, what's called expand the macro, the data that you passed in as parameters is put into the assembly code in line, kind of like referencing a variable. Now, the syntax of macros varies from assembler to assembler, and not all assemblers support macros, but 64task does. And what 64task does is it uses the .macro assembly directive, and the label for the line with the .macro assembly directive is the name of that macro. Anything after .macro is part of the expansion of the macro, and .emd assembly directive at the end closes off that block and ends the definition of the macro. Additionally, on the line where you're defining the macro, you can provide a comma-separated list of names that will be the parameters that your assembly code can pass into the macro to be used inside of it. When your code in the macro wants to reference a parameter, it does so by using a backslash to say, hey, this is going to be a parameter I'm calling upon. And you can either use the name that you gave on the macro line, or you can use a numeral to indicate its position in the list. So like 0 would be the first parameter, 1 would be the second parameter, and so on and so forth. One other little aspect of macros in 64tasks is that you can define labels inside of a macro, like labels on a line or whatever. But that label is only visible and usable within the macro itself. So in programming languages terms, there's a scope involved with a macro, and the labels are defined within the scope of the macro, but not outside of that. And that can be useful in several different circumstances. All right, so that's enough general stuff. Let's get into the actual tutorial example code and see how we can use the stack and subroutines and macros to make our code a little bit more readable and a little bit more reusable. So let's take a look at the source code for the demo. This is going to be pretty much just a modification of what we looked at in the last tutorial. And most of this will look fairly similar. So, again, we have the preamble where we're setting up what processor we're using, and we're setting our start location and all that. But now I've got a new include for this macros.asm file. So let's take a look at that quickly and see what's in here. So I've got a bunch of macros defined, and they're all these things called set AS, set AL, set XS, set XL, and so on. And if you look at them, what I'm doing here is I'm setting up a macro, and in between the dot macro and the dot .emdm, I've got some assembly statements, and I've got just two in these first few. And this one is calling the SEP instruction to make the accumulator 8 bits, and then it's also including that assembler directive we always want to be using of .as to tell the assembler that the accumulator is 8 bits wide at that point. And because we use these sorts of pairs all the time in our assembly code, I've just set up a bunch of macros to make that a little easier to read and kind of clean up the source code a bit. And then I've got equivalent ones for making accumulator long, making the index register short, making the index registers long. And then I've also got, for when I want to set all of my registers one way or the other, I have two macros there that include both the assembler directives that go along with that. So very simple. You can make macros much more complicated. We'll probably see some of those later in this tutorial project, but for right now, we'll just keep these simple. Again, I'm hooking into the Wiki registers, and then I'm setting up some definitions here. So I'm defining some labels. And this first one we've seen before, just where we're going to be sticking the sprite in Wiki memory, in the video memory. But I'm going to be keeping a hold of two variables to track where the sprite is. And I'm putting those kind of arbitrarily in these two locations in memory. These are both going to be 16-bit values because our screen resolution is 640 by 480. We need 2 bytes to store those pixel locations. And I'm just sticking them here in 002000 through 002003. This is a section of memory on the C256 that's not used by the kernel. It's free to be used by a program, so I'm just sticking them there. Next, I have some definitions to two kernel routines that I'm going to be using. I am going to want to clear the screen of the text values, and I want to wait for a character from the keyboard. And so these two routines here are the C256 kernel routines to do those two functions. So this first one here waits for a character to be pressed on the keyboard and returns that in the accumulator. And the second one here is the one to actually clear the screen. Now, we're going to be moving the sprite around, so it's helpful to define some bounds of where we're going to allow the sprite to move. So that's what I'm doing here. I'm defining a minimum y and x value and a maximum y and maximum x value. And then we can go ahead and start our code. So starting off, I want to set things up with a 8-bit accumulator and 16-bit index register. So I call those two macros. So there's how you invoke a macro or how you use a macro in 64 tasks. Different assemblers will have different syntaxes. I believe in 64 tasks you could also use a dot syntax to say dot set AS for invoking a macro. I'm not sure. I just do it this way. And this works perfectly fine. And then now I want to clear this. Once I've done that, I want to clear the screen. So I need to call that kernel routine to clear the screen. Now, if you remember, that kernel routine that's up here in bank 0, so there it is. And all the kernel routines, because they could be called from anywhere in Wiki memory, in C256's memory, those kernel routines have to be var routines. So you call them with the JSL instruction. And so when this returns, the text screen should have been cleared. And now we can go ahead, and this is code I've not changed particularly. Now we can go ahead and initialize the color lookup table and the bitmap data, just as we did before with just a simple copy loop. I have made a change here, and it's not a terribly important one right now. It doesn't really change the functionality. I'm just cleaning up the assembly code a little bit from last time. this little syntax here might look a little strange, this @L. What this is doing is it's telling 64 tasks, so this is a 64 task specific syntax. It is telling 64 tasks the address of that label should be considered a long address. So we want to use the, in this case, the absolute long indirect addressing mode here. If I just had @L like this can actually be ambiguous depending on how things are set up. It can be an absolute address, it can be or absolute index, it can be absolute long indexed, or it could even be what's called a direct page indexed addressing mode. So we need to be a little careful of how we, making sure we're specifying what we want. So I'm going to be getting into the habit of using this @ syntax in my assembly. Not strictly necessary, but it does mean we are doing what we're telling it exactly what we want it to be. So you see I've done that a couple places. I'm doing it down here as well. So now once we've initialized the bitmap and the color lookup table, now we want to show the sprite. And this is going to be, this section here is exactly the same as in the previous one. Once that's done, we want to set the location of the sprite. Now before I just wrote directly into the Wiki registers. Now I'm going to do something a little different. Because we're going to be moving the sprite interactively, I'm going to store the coordinates in those variables that I set up at the top. And so I'm setting those both again to 100 by 100. And here you see I load accumulator with 100. And I store it first in SP0X and then second in SP0Y. And now I want to have a subroutine that I will call repeatedly whenever I want to update the location of the sprite. And that's going to be this SP0 @. So before we get into calling it and all that, we'll get down here and we'll take a look at that. That's here. It's a section here. And so I open, now this is again something that I do, I think this is a fairly good practice, and this is again 64 task syntax. We have an assembly directive .proc. What this does is it tells 64 tasks that the code following is part of a procedure or subroutine named SP0 @. And it kind of does two things. One is it tags that code, and so 64 tasks can do some optimizations. But the second thing it does is that you can define labels inside the procedure. Those labels will be valid for use inside the procedure, but they won't be available or even visible outside the procedure. So it's a way of kind of protecting labels, allowing you to have, you can have a label like done, for instance, where you want to, go and return to the caller from your subroutine. You don't have to say SP0 @done or something like that. You can just call it done, and because it's inside that procedure, it will only be available there. I find that makes it a little bit easier to code. That's just a personal preference of mine. But .proc is followed by a .pend, PEND rather, that marks the end of the procedure. So all of these assembly instructions here, those are all considered part of that procedure. So it's kind of a little blocking assembly directive. So in my code here, I'm going and pushing the processor status register to the stack. And you will notice that at the end, when I go to return, I am pulling the processor status register back from the stack. So these two are paired with each other. And then once I've saved the processor status register, I set the accumulator long. I don't know if the accumulator is 8 bits or 16 bits when I start this procedure. So in starting the procedure, I want to make sure it's long. And so I do that set AL here. It might be in your own personal code that you've got, the coding discipline set up that your accumulator is always wide or it's always small or whatever. So you might not necessarily need to do this. I have gotten bitten multiple times because the code has been using a different register width than what the caller was using and didn't necessarily set it correctly. So I've kind of gotten a little bit aggressive, I should say, about always setting the register widths, when I need, when I don't necessarily know what is going to be coming in. So when I set the accumulator to be long, and then I go and I set the Wiki registers from the variables that we're keeping track of. And when that's done, again, I pull the processor status register and I do a return to the calling return from subroutine, so RTS. Now, because this code is part of my program, because it's included in the same bank as the main code, I can do just a short subroutine, a near subroutine for this, and do an RTS at the end. What that means is that when I call it, back up here in our initialization, I have to use JSR. So I do the jump to subroutine for the near subroutine or JSR here at that section. That also means that SP0 cannot be called from any other bank in memory. So it's got to be called locally. But anyway, once that's called, the sprite should be stored, and it should be shown at 100 by 100. Now, once that's done, I can enter into my loop and start waiting for key presses. And that's what we've got going on here. So I've set up a label, get key. And here you'll see I am setting the accumulator to be narrow again, to be 8 bits wide. And then I call that kernel routine to wait for a key press. And again, because that's a kernel routine, it's a var routine, so I need to call it with JSL. And then I just have a bunch of comparisons. So I check to see, is it a W? If so, I'm going to jump to that label do up. Is it a lowercase w, jump to do up, and so on. So W goes up, S goes to do down, A goes to do left, D goes to do right. If it's none of these things, we fall through to this instruction here, BRA. Now, I don't think I talked about BRA in the last tutorial. It is a branch, so it's like BEQ or BNE and that sort of thing, but it does not check any of the status register flags. It always does the branch. And so BRA stands for branch always. So if none of those keys were pressed, then we will come back to here and we just got to keep looping. And then here we have the actual section to handle what we're doing with the key presses. So here's do up and do down. Do up, because I'm going to be modifying the coordinates, which again is a 16-bit value, I'm switching back to a wide accumulator, or 16-bit accumulator with set AL. And I get the Y coordinate. And because I'm going up, I need to decrement the Y coordinate. I need to take one away from it. That's because the origin of the Wiki bitmap screen is, as is typical with computers, is in the upper left-hand corner. So Y increases going down, X increases going to the right. So we want to go up, we want to decrement Y, we want to reduce it. And so once we've decremented it, then we want to check it against the minimum value. As long as it's greater than or equal to that minimum value, we want to go ahead and process that. So what we would do is we'd come down here to the set Y, we'd store it back in the variable, we would then call sp0 at to actually set the sprite's location, and then we branch back to get key to get another, get another key press. Do down is very similar, but instead of decrementing, we're going to increment, and we're going to check against the maximum Y value. So is Y greater than or equal to maximum Y? If not, so we haven't reached that boundary yet. If we haven't reached that boundary, we want to set Y again. Otherwise, we want to ignore that key press and get another one. Do left and do right are here. They do almost exactly the same thing, except they're working with the X coordinates. So do left, we want to decrement the X coordinate. do right, we want to increment the x coordinate, and we have a set x here again to actually set the value and call out to update the Wiki registers. So here you see we've got a couple places where we're calling that subroutine sp0 at. And again, because that's in our same bank, we can call it with the near call. And then there's that routine again. And that's really it for the code. So what we should get when we run this is that the sprite should appear, and then as I press the different WASD keys on the keyboard, the sprite should move around for us. Not a very exciting game, I admit, but it's another baby step. We have some interactivity here. So let's pop over and look at this on the actual C256 and see what it does. All right, so I've just sent the hex file over to my Phoenix. And I'll pop into the monitor here. And I'll start the code. There you see the text screen has cleared, and I've got my sprite. And now I'll start pressing some keys, and you can see the sprite actually moving around. Not the fastest animation in the world, I admit. So you can see if I go up towards the top that it stops moving at that point. So we've reached that limit. Same for if I go over to the left. And you might have been wondering why I set the values that I did for the maximum and minimum coordinate values. The upper left-hand corner for the sprite is where its origin point is. And the coordinates that origin point can go on to can be, not just in this black area of the screen that you see here, but they can even go underneath the margin, underneath the border, and there's even a little bit of room outside of that. So I set those coordinates so we would be restricting it to this section of memory that's here in the black area of the screen. But yeah, anyway, so there you go. Works pretty simply, and it's interactive, and we now have seen how to do macros, and we've seen how to do subroutines, and call out to kernel calls, so how you do a far call as well. So I hope that is useful to you. I hope you found this interesting, and thanks for watching.